One of the most important things that an electrical or computer engineer might need to do in digital logic or in looking at digital circuits is to try to find out if a very complex circuit could be reduced to yield a simpler circuit. You can imagine a circumstance in which you could do this very complicated series of actions, or you could do this much simpler series of actions. You know, can I scoop 1 teaspoon at a time out of this container into this other container, or can I just pour the whole container? As an engineer, our job is to try to make things be as efficient as possible. And so if two functions are perfectly equivalent to each other, our job is to choose the better one, is to find the simplest one. One of the tools we can use to do this is known as perfect induction. And so perfect induction is a tool that simply allows us to verify that two functions are exactly equivalent to each other. And how do we do that? We can prove that if the outputs of every row of their truth tables are exactly identical to each other. And so that's really what we're going to look at here with perfect induction. I want to prove the equivalence of two functions. I want to look at x or y, and I want to compare that to x or not x and y. And so you can see over here, I've got the same 4 rows of the truth table. And if I look at x or y, well, if it's 0, 1, 1, 0, or 1, 1, all of those are going to be 1 only if both inputs are 0. That's the only circumstance in which the output will also be a 0. The second half is a little bit trickier because I have to consider what happens. I have to look at what is x bar. So first of all, I have x, and I invert each of those 4 numbers to get x bar. Then I take x bar ANDed with y. So I'm taking these 2 columns here and ANDing them together. I get 0, and then here, this is the only place where they're both 1, and so therefore I get a 1, and then here there's 0 and 0. Then if I'm going to OR x with not x and y, then I'm ORing together the left-hand column, the first column with the 4th column. And so that gives a 0, and then I'm ORing 0 or 1 gives a 1, 1 or 0 gives a 1, 1 or 0 gives a 1. And so this is x or not x and y. And so if you look at those 2 shaded columns there, you can see that they are exactly the same in every single row. And if they're exactly the same, perfect induction says that those 2 equations are exactly equivalent to each other. So now you have enough information to solve the perfect induction example. I'm going to go ahead and show you one more method before I stop this video, and that is using a Venn diagram. Now, Venn diagrams are awesome because they're visual, and our brain is very good at visual things, and so we can tackle a visual problem very easily with a Venn diagram. I want to, in fact, do the same exact problem that we just did. So I want to consider how can I prove using Venn diagrams that x or y is equal to x or not x and y. Well, if I have 2 circles that are overlapping each other here, I'll call the left one x and I'll call the right one y. Well, if I'm going to do the right-hand side of this equation, the right-hand side is going to be x or, and so when I say x or, well, that means immediately shade the whole x circle. X or what? Not x and y. Not x and y is just that portion of y that is outside of x. So I need it to be inside of y, but outside of x. And so this is sort of like a little weird-looking Pac-Man that's going from right to left. It's this portion of the circle. If you're watching this in color, it's blue, that is outside of the red circle, but inside of the other circle. And when I take those 2 together, what you'll notice is that I've now shaded in this entire sort of double circle. It kind of looks like a pair of binoculars or like a MasterCard symbol. And that is everything that is covered by either x or y or both. And so I've covered both sides of this equation, one of them by constructing it, and the other one by saying, oh yes, that's exactly the same thing as covering both x or y. So we're covering everything that's in x and everything that's in y. And so by doing this graphically, I've proven that equation a second time. Of course, I'd already proven it once, but still it's nice to be able to see it a second time as well. Now, Venn diagrams are very useful, and they provide us good, strong visual proof of a statement's validity, but it's important to realize that they can work well with 2 variables or even 3 variables, but when you get to 4 or more variables, it gets really hard to use a Venn diagram. Okay, so I'm going to wrap this up here. You've got enough information now to solve the Venn diagram example. Don't forget to go back and do the perfect induction example as well.